problems where we get weird, harder problem, we get weird angles. We've got 3 vectors to reconcile here, but remember, we're just going to use our strategy for adding vectors by the process of vector resolution, which is, in other words, the table method, right? So what are we going to do? We've got a ship that's cruising along. They give us the speed and direction relative to the water. The current is flowing due northwest at this. They give us current, or they give us direction and magnitude there as well. They give us a passenger rides a scooter along the deck at this speed and angle, okay? And so they want us to know what's the velocity of the scooter relative to the earth or the shore, okay? So how would we, first of all, let's think about this just conceptually before we jump into any of the math. How are we going to do that? We've got these 3 vectors, right? Think what these vectors represent. The first one, let's just look at this in terms of those subscripts that we talked about before, right? The first one we've got, let's just for now call it V for velocity of water relative, of ship relative to water, right? So we could say S sub SR, right? Okay, we've got the velocity of the passenger riding a scooter along, oh sorry, the water is flowing. So what's that relative to? That's the velocity of what? There's a current. So the water's flowing, moving relative to what?
The shore.
The shore or the earth, right? One or the other. Because I've already used the subscript S, I'm going to use E. So that's the velocity of the water oh, I should have been. Why did I put an R there? I should have been a W, shouldn't it? All right. That first one, velocity of the ship relative to the water. Next one is the velocity of the water relative to the earth. And then the last one is what? The velocity of the passenger relative to the ship, right? So if I added all those up, and vectors are commutative, it doesn't matter the order in which I add them up. But if I were to put this one in the front, look what we'd get then. We'd get velocity of person relative to ship plus velocity of ship relative to water plus velocity of water relative to earth. Well, what was our little trick here? We said that we could cancel those two, right? Those are the common medium. And that would give us person relative to water, but then here the water and the water cancel. And so the sum of this is just going to be the vector of the person relative to the earth, which is what we're looking for, isn't it? Right? And you may not have even needed to do that. It just makes sense that if we're adding those vectors up, then ultimately we're wanting to know scooter, or I call it person, relative to shore. Well, we have our earth. We have the vectors that are able to, they're able to relate those 3 different shore, water, ship, 4 things, and person, right? We've got the vectors that interrelate those 4 things, right? So by adding these vectors up tip to tail, we're getting the velocity that does what we want it to do, right? Now the hard part is, let's adding up, or the arduous process. I'm not going to say it's really hard in the sense that it's very difficult, but it's easy to make a mistake whenever you have a long process like this, right? So now let's go through the other part of this. Let's add all these up. So let's take this first vector and let's make it, what if we make this one yellow? Okay, we can just knock these off one at a time. We never have to add any of these vectors up tip to tail until we've broken them all up into components, right? So we're just going to take each vector independently and break it up into an x and y component, okay? So how does this one fit if it's 48 degrees west of north. How am I going to draw that vector on this set of axes here?
Second quadrant.
So second quadrant, isn't it? And where's the 48 degrees? If it's west of north, good, we're starting north and we're sweeping out angle to the west, so that's going to be theta right there, isn't it? Right? So it's going to look something like this. That's going to be 48.0 degrees, right? And the magnitude of the vector is?
9.7.
Okay, 9.7, oh, 09, sorry. Right. Say it again. The magnitudes, vectors have two parts. They have a number, which is the length of the vector, the magnitude, and then they have an angle, right? So if we wanted to break this into components then, what are those components going to look like? We're going to get, I guess we're using this angle this time, right? So what is that angle right there going to be? We can call this, how are we going to label this one? Let's label this is velocity of the ship. Okay, so we'll call this, what do we call this? B for boat. So this is B sub X or Y? Y, okay. And this is going to be, we add those two up, tip to tail, that is B sub X. Okay, what are the formulas going to be for those by SOHCAHTOA? And Y? So B sub Y is going to be what? Now think about how we talked about this. We know when we multiply by sine or cosine, are we making a number bigger or smaller? Smaller, right? Because and we should. We're going to take the hypotenuse and break it into X and Y components, which are smaller. So we're always going to start off with, this is our shortcut. We could just write out the SOHCAHTOA relationship and solve for B sub Y. But because it's a component, we know that we're always going to start off by multiplying the hypotenuse, which is the magnitude of the whole vector, times what?
Cosine.
Cosine.
Cosine 48 degrees.
Okay, good, because it's going to be the angle that's adjacent to the angle. Adjacent angles by SOHCAHTOA are linked to cosine, right? Okay. So 9.09 cosine of my angle, which is 48.0 degrees. Okay. What about B sub X?
9.09 sine 48 degrees.
Okay, 9.09 sine 48.0 degrees. I'm not going to put an SIGN sign on that yet. Not until we go to the table and we interpret it in terms of our positive X and Y directions. Okay? Well, how about if let's do that right now, actually. So we've got these, we'll just start the process. So we got this first vector. So we could go over to the table, and let me grab a picture of this, at least part of this here real quick. So if we take that stuff, isn't that cool? Don't you wish you had some toys like that at home? Okay, so there's the first part. So what goes where? So this is vector B for boat. What's the X component?
9.09 sine.
Okay, positive or negative? Negative, how come?
Goes to the left.
Pointing in the opposite X direction, negative X direction, right? So up here we're going to do negative 9.09 sine 48 degrees. Now I won't write the point 0. Okay? What's the Y component going to be? 9.09, positive 9.09, right? Cosine 48 degrees, right? Okay? Good. So now I'm going to get rid of that so we don't clutter things up too bad. Oh, what did I do? No. I want to do that. Okay, back to the other page. So we did our first vector. Okay, next one. Let's make this one green. So now we want to know, looks like current flows northwest at 6.25 meters per second. Okay, so that's, we're gonna call that water, how about, right? This is the direction of the water. Okay, so what's northwest? So that's 45 right there. And it doesn't really matter which one we choose to be 45 this time, does it? You can pick. Which angle you want. I mean, if it's northwest, that's 45 and that's 45. Which one you want, Mark? You want the up one?
The same one, yeah.
Okay, same one will do. Okay, so there's our 45-degree angle. The magnitude is 6.25. Okay, so then we can break this up same way. It's going to look pretty similar. So now we get W sub Y, W sub X, right? And this is kind of the same concept, isn't it? We could probably fill these in pretty quick. What am I going to get for W sub X?
6.25
Right?
Do you not write the negative?
No, we don't, I wouldn't yet. We'll put that in on the table based on the direction they point, okay? I mean, I suppose you could, but the reason I don't is because these are just reference triangles, right? The triangles, the triangle by itself just has some components, but when we put those together in terms of the context of adding up the components in the XY plane, that's when we attach the negatives and positives, right? And then this would just be 6.25 cosine 45, right? So now let's take this one. So let's take that one, and we can plug in, we get vector W. Now we can interpret the directions. The x component's negative, right? Y component's positive, everybody agree? And it's cosine. Okay, last one. So let's scoot back over here, and now we've got the scooter. So it's traveling 3.72 meters per second at 31 degrees south of east. So what's that look like? So that's this guy. Okay, he's going to be light blue. So where's he go? Okay, south of east, so that means we're starting at east, and we're sweeping out that much angle south, right? So we're going to end up with something like that, where this will be our 31.0 degrees. The magnitude is 3.72 standard units, right? We'll break it into components. What do we call this? Person, how about? So we'll call this P sub X and P sub Y. What's P sub X this time in terms of SOHCAHTOA stuff? Ahmad, what's that one going to be? 3.72 to make it smaller, multiply by cosine, because it's adjacent, right? Good. Right? Okay, right. Does that make sense? So we know that, and once again, we're skipping some steps here, right? The steps, let's just go through those steps, and then just so we can see. So if we were going to start from scratch with the SOHCAHTOA relationship here, we would know that we would use, we're trying to link this side to the side that we know, right? So relative to the 31-degree angle, that's adjacent and hypotenuse, right? So SOHCAHTOA tells us that cosine would be the appropriate relationship we get. Cosine of 31 degrees equals the ratio of adjacent, which is p sub x, over hypotenuse, which is 3.72. If I solve for p sub x, what do I get? That, right? We always are going to get something like that. If we're talking about a component, it's always going to be the magnitude of the hypotenuse times either sine or cosine. Multiplying by sine or cosine is going to make it smaller, right? Which the components would need to be. So the shortcut you can always take is, okay, whole thing, hypotenuse meaning whole thing, times, how are we going to make it smaller to get a component? We're going to multiply by sine or cosine based on SOHCAHTOA, okay? So what's going to be p sub y then? Good, sine 31, okay, and now we can fill in the last vector row, right, of the table. So okay, so we call this vector P. And p sub x, positive or negative? Positive. Okay, p sub y? Negative. Okay, so now we're done with the previous page. All we have to do here is come up with the components of the resultant vector, right? The resultant is going to be when I add up these three vectors tip to tail, but we're just going to add up the x components and the y components tip to tail, right? So we'll call this R for resultant. And whatever we get here is going to be the x component, right? Whatever we get here is going to be the y component of the resultant, okay? So then all we've got to do is just add those things up. Now notice that we haven't turned any of those into decimals yet, right? Because we don't want it. We want to keep all of the information in the calculation, right? We'll only round once at the end. So here's where we'll just pop up our graphing calculator and watch how, I think we've gone through something like this before, but let's put it all together in this big ugly problem now. So we want to figure out what's the sum of all those things. Okay, so we'll just go negative 9.09. I checked, I'm in degrees mode, by the way. Make sure you always check that. 9.09 sine 48. Minus, right, minus 6.25 sine 45 plus
Degrees.
3.72 cosine 31, okay? And when I hit enter, I'm going to get a big ugly decimal, right? That's in our calculator. We'll call that a calculator number. But that calculator number is approximated by negative 7.96-ish, right? So I'm going to do this. Right? Okay. Meaning we've got that actual number in the calculator. Okay. So now we got to move over and do this guy, right? Question?
Yeah, can we just round up to 210?
Well,
Oh, negative 8, my bad.
No.
But we don't want to yet because we're going to be using these numbers still in calculations,
Oh.
right? We've got them. That just reminds us what the number is, but it's on our calculator. Okay. Now look how easy this is. I'm going to go up. This is a great trick. I'm going to go up and grab this calculation, and all we've got to do is go down and edit this calculation for this sum, right? So we'll hit second left to go all the way over to the left. This one is positive. So I'm gonna go ahead and delete the negative sign. And notice all I've gotta do in each case is just flip the trig function to the other one, right? If the x component is given by sine, then guaranteed the y component is given by cosine. Like that, right? Then the next operation that joins the terms is plus, so we'll overwrite the minus with a plus. And this time, instead of a sine, we need a cosine. The next operation, instead of a plus, is a minus. So we'll overwrite that, and we need to switch from cosine to sine of 31. How easy is that, right? You can just recycle that calculation every time. So this gives us a calculator number of roughly 8.59-ish, right? That's the calculator number. And so now let's take those and do something with them. Okay, so if I've got the components of my resultant vector, you tell me, how can I turn this into, oops, how can I turn this into resultant vector? So if the overall, the net x component was negative and the y component is positive, first of all, like when I even just build the xy axes, I always try to give myself lots of working room in the quadrant where I'm going to be, all the business is happening. So where's that going to be? Quadrant 2, right? So let's put something like this then, right? So now let's add these components. So I know we're going to have an x component of negative 7.96. Okay, it doesn't really matter if we get this right or not. Not that it matters, but let's go ahead for our resultant. Our resultant's going to be in this quadrant. Let's go ahead and use the upper of the two angles as theta. And you'll see why. I mean, it's not a big deal. Either way would work. So let's start with then the y component. And let's add to that the x component. Doesn't have to be drawn to scale at all. Right, so what are my magnitudes then? Notice the directions: positive in the y direction, negative in the x direction. So this is the one that's roughly 7.96 in length. This is the one that's roughly 8.59. So what's my resultant look like then? Where's it start and where's it end? I'm going to start there, but where does it end up? That make sense? Okay. So here's the resultant. How do I find the magnitude? Pythagorean theorem, right? Square root of that squared plus that squared, right? That's calculator work. So let's pull up our calculator. We've already got those numbers stored, right? Just maybe clear over here, I guess, about this. Okay, so we just want to do the square root of that number, which is right there, right? Because it's negative, I'm going to go ahead and put it in parentheses. Right? It's always safe to do that. So that number, close parentheses, squared, plus that number right there, squared. Everybody agree? Hit enter. There's my magnitude. Okay, I haven't rounded once yet, right? I've carried all the accuracy of all my measurements and calculations out, right? Okay, so I can now
I can now round that answer if I want to, right? Because one of the things we're looking for is what is the final result velocity? So what is it? I think we were able to keep 3 sig figs, weren't we? The original problem? Pretty sure, we can go back and check, but I'm pretty sure it was 3. So what would that be?
11.7.
11.7 meters per second is the magnitude. Now how about the direction? How am I going to find the direction based on this right triangle I constructed? Everything I need now comes from the resultant row of my table. What do I do? Arctangent. Okay, so let's call this one the theta, right? Because that's the one that's inside our triangle. And so how is theta defined? Well, we can skip this step. Let's show it one time. We know that arctangent, or the tangent of theta is what ratio in this case? Opposite over adjacent, so it's this number, right? Over this number, right? But we're trying to find theta, so we always know that we're going to take the arctangent of both sides. So I would say you can skip writing that down. Yes, ma'am. Yes, sir. Sorry.
Would the 7.9 be negative in that?
No, you don't want it to be, because once again, see, and this is kind of why we don't want it to be, because now we're just dealing with now we've switched gears. We're just in geometry mode, and we're just trying to find out based on some right triangle, what's this angle going to be? Well, the sides of a right triangle can't be negative in length, right? We'll interpret the answer based on where this triangle sits in the XY plane, right? But the only places our negatives should show up would be up in the table, okay? Because we would get a weird answer if we tried to do a negative, and we might sometimes get wrong answers if we do that, okay? Or it might be undefined. It may not be defined for the calculator. If it's not in the principal domain of an inverse trig function, the calculator won't do it, okay? So we could skip down. This is kind of the lead-in step, but we're always just going to take the arctangent of both sides to get rid of the tangent, right? And so we know we're always going to end up getting arctangent of the ratio of opposite over adjacent every time, right? And so that's going to be the 7.96 number over the 8.59 number. So that also is just calculator work. So we'll pull up arctangent right here. And we're going to take the ratio of the 7.96 number, but we want it to be positive, right? So what are our ways of doing that? I mean, how do we, the number up here is negative. What are my options to make it positive? I could multiply by -1. I could absolute value it if I want to, right? Or I could just go in and edit the number by deleting the negative sign. Take your pick, right? I like just deleting the negative sign myself too. So we're just going to go up and grab this thing. But you got to be careful to do that, right? Because you want those numbers to be just the magnitudes of the components. You want it to be positive. So we'll grab that, and then we'll just scoot over, oops, and make that, just delete that negative sign. Oops, second right takes me all the way over. Divided by the 8.59 number, which is already positive. Okay, and it gives us back 42.92 blah, blah, blah. To 3 places, what is that angle then? 42.9, okay. There's something else that could happen with this though, which is kind of dorky. 42.9, okay. The way that we need to answer this question is though, what's the angles, the magnitude of the angle swept out from east, right? We want the number of angles north of east is the way it's worded in the question. So 42.9 is not the correct answer.
Subtract by 90.
90 plus that, good, because we'd have to start, right, we're starting here, and we're gonna sweep out that whole angle, which is 90 plus the extra 42.9. Now, what happens to the number of, to our answer if we're keeping 3 sig figs and I add 90 to this? We end up, if I add 90 to that, I get 132.9. But how many can I keep?
3.
3, so it becomes
133.
133. Right. Okay, make sense? So then, the whole theta is about 133 degrees. So now let's just go back and input these and see how we did. So you guys, did you write these down, I hope? Do you remember what write them down real quick. We ended up with 11.7 meters per second was the net velocity, right? Net magnitude of velocity. We could call that speed, couldn't we? Right? Does that make sense? We call that speed because it's the magnitude of velocity. And our complete angle was 133. Hey, you guys, come on in. The complete angle was 133, so write those down. And we'll just go back and check that. Move. I think I've still got this problem up. Okay. Somewhere here. I'm hoping I do.
I agree now.
Let's see. Is that us? Oh, we gotta check it. Here it is, quick. What was it again? It was, say it again. One person, 11.7. Okay, we're just adding magnitudes and then 133.
Yep.
All right, let's check it.
It's wrong. It's wrong. Oh, right. Oh.
That's right. Woo, we did it. All right, good work.
Instead of using your guys' stuff, I did it on mine, and when I put in my answer, I put 4.69, and it told me that the right was 4.7. So I don't know why that, because there's 3 significant digits. Now.
Right. Okay, it must have been the way we added it. We'll look at it. We'll look at it.
I didn't say on the question that it was 4.1. I was just wondering why, like.
Okay, it must have been during the calculator work. We'll check it out.
Oh.
Yeah, bring it in. Hold that. Can you? I mean, like we'll look at it
I mean,
again.
I was just, because like I don't know why it told me it was only 2 significant digits when.
Yeah. All right. You guys hold on for just a second. Oh, sure. Is Glad pop in? Pop in anytime? Sure.
It sounded good though.
It's easy. What's wrong? No, go ahead and leave him here for just a second. We will, but I'm gonna have to do something else. Okay. Hey, quit touching my boob. At 2:37 p.m. I need to go train for work. Brett?
We're not getting these.
You will, but not right away. Okay, so